So, thank you very much for your introduction. So, my name is Thijs Romans. I want to do a talk on advancements in analysis methods for composite automotive applications. So, I represent the company VIRO. VIRO is an engineering firm with 800 engineers distributed among the Netherlands, Germany, and Austria. The main headquarters is in Hengelo. But actually, the department that I represent is the biggest one. It has 270 engineers. And I'm the group lead of the engineering analysis group. And this is a group that uses the scientific methods, so complex computational computers. And we try to solve technical questions or technical difficulties with all types of computational methods. And before I start, I want to make a big thanks to Robin Borger. So we presented, or what I'm going to present is a test case, and Robin made this one. And also my co-author, Jos Dule, which is my right hand and helps me with many topics, and they both deserve a big comment on this presentation. So first of all, I have 3 slides, and in these 3 slides, I want to comment on the problem that I see, my method that I propose to solve this one, and also the goal that I envision. And then I talk about my test case. So my problem is, normally you always get the question, at least in the commercial vehicle industry where we work for, it's always the question, when, where, and how can we implement composites, and when can they outperform their metallic counterparts? It's always a problem. Not knowing if it's suitable. You have many considerations. I've listed them here. You have the cost, geometric complexity, life expectancies, low cycle fatigue, high cycle fatigue, strength is an issue, sustainability, of course, in this medium that we are discussing right now is also a big topic. And if you really want to start exchanging the current components in a car or in a commercial vehicle and implement then a composite, then there are many considerations. Of course, that's what I'm trying to say. And what I see is that you have the supplier. So the talks that I've heard so far, I believe, are all on the side of the supplier, so the material side. And the supplier I have now here on the right in my picture then summarized as composite manufacturers. And on the other side, you have the end user, which is the automotive manufacturer. And both sides, they are differently focused. So the supplier is focused on his product, what he has lying on his shelf. And the automotive manufacturer is really focused on his application and simply wants a tested and functional solution. And there is a gap between those two worlds. And what I propose is that you will see on my next slide, is that with a CIA-driven design, we can bridge this gap. So this is my second slide. It goes into the method that I propose. So CIA-driven design using sophisticated computational techniques as part of virtual prototyping. So virtual prototyping is not using a lot of testing. Of course, testing is a factor in this also. You need to know your material. You need to have certain specifics about this material. But so we as an engineering firm, as a group, we use many different computational techniques. For instance, most widely known is probably finite element modeling, which is FEM. But also multi-body dynamics is something that we use often. Multi-body dynamics is used for vehicle dynamics to really get a feel for the loads that are occurring on a car, and time dependent, of course. A multi-domain physics system, these 1D simulation, for instance, LMS AMSIM, or more known, you have these topics like MATLAB and Simulink. What we do here is, for instance, evaluate electrical drive lines for customers that we have, going from a combustion engine to electrical drive line. Their multi-domain is a topic that's really interesting. Also something said already, noise, vibration, and harshness, because the car is changing from a combustion engine to electrical car. Different topics pop up. The noise is different. So what kind of effect does it have on my acoustic? That is something that we also do with these computational techniques that we have. NVH is that solution. And then there are computational fluid dynamics, CFD. And that is, for instance, flow-induced forces. that can also be then transferred in finite element modeling, but also there are thermal topics. In any case, what I'm trying to say here is that many times we as an engineering firm step up on the scene as a third party for the verification. We do this for trucks, for buses, for agricultural vehicles, to really, the end user is not allowed or can only go this far, but needs to have a third party verification who more or less compares his meat or yeah, how do you say, evaluates his meat. And the CAE-driven design, as an engineering firm, we also do this to really quickly come to good components, development, and engineering. That is also on the other side. And if you combine those two, you can see many topics: loads, optimization, thermal imaging. We use standards, strength, cost engineering. Those are all part in our portfolio. And so the CAE-driven design and third-party verification, they come from top to bottom, and application and material knowledge comes from left to right. And there I can see in combination of all sorts of expertise coming together, where through we can think we can bridge the gap between the supplier and the end manufacturer. So my goal is to combine the material knowledge that we have, the automotive application knowledge that we have, working for trucks, bus, car, agricultural vehicle manufacturers, and also our strength in scientific computing on all these different topics that I showed you or that I discussed before. And if you will do this, then you can really identify, design, and verify the utilization of composites. And that opens up many possibilities. For instance, if you would have 5 metallic components and you would have the idea, maybe those 5 metallic components, I can make one composite part of that. But yeah, what kind of loads are there? Is it possible? How is it with lifetime and fatigue and stuff like that? This is all possible in the virtual prototyping. Also, points, durability, sustainability, the choice maybe going from a turbo set to a thermoplastic, thermoplastic which are more sustainable. What would this involve? Maybe on strength assessment, that is also then a topic that we look into. We are very strong in this vehicle safety, so crash simulations. Can, for instance, a part of a chassis be exchanged for a composite, yes or no? And how do you evaluate that? Cost prediction, these are all possibilities that's now come into play if you combine these 3 things. And the supplier has the material knowledge, we as well also have the material knowledge. The end user have the automotive application knowledge, we as well have this. So, and the scientific computing comes in there as well. So that is my goal, and this is the goal of my group as well. So what we have prepared is an example case, a very simple one, so nothing really sophisticated. I can't, unfortunately, not show you any type of work that we're doing currently, but this will be an exemplary case. In this case, we will take this car on the right side. It's a Ford Taurus, an older model from the 2000, and what we'll do is we do a rollover case. And the rollover case that we are trying to simulate here is based on the American roof crush regulation. So on the right, you see this image, this plate will be indenting this chassis, and the regulations prescribe a certain amount of force that it needs to support eventually. And what we want to do is make very simple comparison between the steel variant, so the original variant, and the composited variant, where we exchange a part of the current chassis then, or the current chassis, the chassis from 2000. So a big part always in these type of simulations in the virtual prototyping environment is the material definition. Now, we in this test case will keep it as straightforward as possible, but always if you make a material model, there are 3, especially in composite, 3 parts. You have the material definition. So in the material definition, you would put, how do you say, all kind of material properties. In the ply definition, you specify thicknesses or other kind of topics that are involved with the ply. And the laminate is just a combination of different plies, how they are orientated, their build-up. These are for composites 3 things that need to be taken into account. And this is the most basic setup. But you can add many more complexity here. So this now is still not based on any failure and damage, but you could incorporate that based on strains or based on the amount of work that the material is performing. Strain rate dependency is also something that can be put in there because we're looking into sort of a crash type of simulation. Speed of the plate will be very high, so strain rate dependency will be high. Materials will behave differently because of they are indented very quickly. Also, you can have laminate position dependency, where apply is somewhere in this laminate also makes up for, will also have an influence. But you can still add many more complexities. I do not want to go as far as the academic side. For instance, the universities, they go on molecular level. This is not what I looking forward to. I still want to make it efficient and not go into too much detail, but this still allows me a lot of fine-tuning already, and it will allow me to make a good comparison between the current, the metallic variant versus the composite variant. And what I also want to subscribe here or emphasis here is that VIRO is currently investing time and resources in this topic. So I probably am invited in this consortium right now because we are planning to do a 20-month of investment with one of my workers to do all sorts of testing on thermoplastics. So to have this material definition really cut out for us so that we also can verify that sensibly and also make good propositions to our customers in the commercial vehicle market. The FA model here is a very simple one. In this case, we have the Ford Taurus chassis, and what we will do is the light blue that here is on the image, we will exchange that for a composite. Now, also this composite is really straightforward. It's a unidirectional carbon fiber, so nothing too fancy. But what it is an explicit calculation, a radius. So the program that we use is the same program that all the other car manufacturers are using for crash simulations. And so HyperWorks that we use right here in this part now is the standard for this type of simulations. You also have LS-DYNA, for instance, but this explicit variant is very well used in this type of situations. It will also be time dependent and there will be nonlinear. It's really a crash simulation. And one thing also that needs to be stated here is that all the connections are very basic. So we do not look into the wells and with too much detail. Everything is more or less oversimplified, but still all the connections behave inelastically. So there is some realism there as well. So it's not too much away from reality. So then if you are then starting the simulation, you have this plate, it starts indenting the chassis. And on the left, you see the steel variant, so the original chassis. And on the right, you can see this composite variant where a side of the, or a part of the side structure has been exchanged for a composite and where the roof has been exchanged for a composite. And you already can see in these images that the steel component is deforming more than for instance here, the composite variant. And if you would end the simulation really at the end, and so this is the deformation at the end of the simulation when the plate conform regulation is 127 millimeters indented. Yeah, you can see this wrinkling occurring in the steel variant. You can also see that yeah, you will have a little bit more deformation, more buckling, and with the composite that's not the case. But this is just very simple kind of result. This is also not the result that we're really looking into. What we really want to know is how much force can the steel variant, the original one, support, and how much can the composite take up? If you look at this, at 30 kilonewtons, you can see that the steel variant is at its peak. And this is when a displacement of now, let's say 61, 62 millimeter has been undertaken. And the 30 kilonewton for the composite variant is earlier, so it behaves better, the composite variant. And it will even go up even further. But already you can see, I've wrote it down here on top, the regulation from 2009 prescribes that at least 3 times its own weight needs to be carried. So in 2000, when the Ford chassis was designed, the regulation was different. It needed to be 2 times, so exactly where it needs to be right now in this image. But yeah, the regulations have gone up. But still, also with the composite variant, that is what I wanted to say, you're not there. So there still needs to be some tweaking. And this is something that we didn't know beforehand. It's just an exemplary case. You can go into much detail, but now If a customer would want it to go and would say like, yeah, I really want to do this, I want to implement the composite, how can we do this? Then there are different ways to go about. But for that, I'll come to a slide later on. If you're looking now exactly at 30 kilonewtons, so on the left side, you can see this 45%, and there is the intrusion survival space here. So the composite variant is way better, functions way better. Also, if you look, for instance, the absorbed energy is also better for the composite. But I have to make a critical note here. It's an exemplary case. The critical note is that failure and damage is not taken into account yet. So on the right, you can, for instance, see many elements are red, and normally in this type of material, 0.1 strain would be the maximum allowable strain. As I said before, in this material definition, you can go into much more detail and implement this, and then those elements would have taken out consideration. This is my final slide before my conclusion slide, so please allow me to explain this, because I think this is a very important slide. This is also the one that comes into play with the advancements in simulations. So we started with this initial model, which is a steel variant. One could have said like, yeah, we'll start with a composite throughout. At that case, you can also do numerical methods or do an iterational process. And if you would do this iterational process, then you would have a sort of a topography optimization where you can say like, yeah, thicken where it needs to be thickened, where there is a lot of stresses, and thin it where it's possible to thin. And this is no guessing game. The computer does this. This is a sort of an algorithm. It's a numerical method, but you can make restrictions on it. You can say like, if you implement material, then implement a layer of 0.4 millimeter thickness. And if you implement a layer, then take a surface of 20 by 20 centimeters, for instance. And what you can see on the right is also an iterative process where you shuffle the layers. The orientation of the layers is shuffled. So you start out with a very simple setup, but there is no guessing game involved anymore. You get, in the end, the best possible load and weight optimized composite component. So my conclusion slide then at the end. What I've tried to explain is that the knowledge gap between supplier and end users, I think, can be bridged by the CAA-driven design. Virtual prototyping will be very helpful for identifying, designing, and verifying those functional composite components. And in my last slide, I tried to explain that through numerical methods and iterative process algorithms, you can really get a load and weight optimized composite and no longer have this guessing game and these long cycles of development. And that is where we would like to step in and also are investing the next 20 months. Thank you very much for your attention. That's it.